Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 40+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify innovative applications, build skills and standards, and advance partnerships to solve global challenges. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor.
Yeah, welcome everyone. Today it's my pleasure to introduce the presentation of Philippe Schwaller, who received a bachelor's and master degree from EPFL in Switzerland. And while working for IBM Research, Philippe completed a master in philosophy at the University of Cambridge and a PhD in chemistry and molecular sciences with the Raymond Group at the University of Bern. In February 22, Philippe joined EPFL as a tenure track assistant professor at the Institute of Chemical Sciences and Engineering, and he leads the Lab of Artificial Chemical Intelligence. And Philippe is also a core PI of the NCCR Catalysis, a Swiss Center for Sustainable Chemistry Research and Education and Innovation. And Philippe is an Alice Scholar and a member of the Alice program, Machine Learning for Molecule Discovery. And today we will hear a presentation titled Teaching Language Models to Speak Chemistry from Design to Synthesis. Philippe, the floor is yours.
Thank you very much for the super nice introduction and for the invitation to speak with all of you today. And let me just see. I'm not sure if you're like kind of aware of that, but almost everything around us is related to chemistry or materials, from like the pharmaceutical to the food that you eat, to kind of the materials your phone is made of. Everything is kind of made through a chemical process. And if we kind of think of chemical and material space, it's nearly endless. Like kind of for drug-like molecules, there's an estimate of 10 to the power of 60, which is more than stars in the universe. So my lab at EPFL is kind of thinking about how can we accelerate the kind of the discoveries that we make in the materials and chemical space. And we think a lot about what kind of molecule do we want to make with use cases in catalysis or drug discovery. And the end goal should always be experimental validation. This is kind of, we are purely digital lab, so we cover that often with some collaborations or external partners. But one reason this is not done that much in machine learning is that it's actually quite hard to like kind of synthesize a new material that has, or molecule that has never been made before. So parts of the group is also working on how to make new materials, how to like plan a synthesis to kind of go from commercially available building blocks to the target compound, how to optimize synthesis steps, and so on. I will just start a time as well, so I get a bit the information of where I am. Like, and on those topics, I will highlight a few publications that we had in the recent years, going from really small language models that are super efficient at learning a target property profile to like how we use large language models agents for chemical research. I called my talk teaching language models chemistry, and this goes only with text-based representations of molecules. And one that is famously used is SMILES, which was developed back in the 80s. And here you see kind of a SMILES represented molecule. You can follow kind of, if I take the laser pointer, you can follow the carbon atom, nitrogen, carbon, and so on. Then the branch here is done by the brackets, and you can open a ring with the one and close it later on. You see also how it goes through the molecule with the different colors here to give you an impression. And using that representation, back in 2018, while I was working at the University of Cambridge and with IBM Research, I introduced the first transform model in chemistry. And back then, we were using it to do reaction prediction. So basically, what we did is to map reaction prediction, where you want to predict the most likely product out of a set of reactants, to a neural machine translation task, so that you would now not translate from one language to another, for example, German to English, but you would translate from a precursor space to a product space. And this worked reasonably well, surprisingly, so that I continue to work on language models for chemistry. But now that you see how molecules can be represented as text, let's start with kind of the design part. The most interesting thing for me, like kind of in designing novel molecules with desired property, is really to kind of design something that has a target property profile. And often without having any molecule representing this target property profile, something completely novel. And if you have very limited data, one of the typical strategies is to do kind of transfer learning, start to teach a model like how to generate a molecule. What do molecules look like? Can I generate valid SMILES? And in drug discovery, you could take Campbell as an example, as an initial database. And if you have even a small data set of like similar molecule to what you want to generate, you can do fine tuning. But if you don't have that, but you have kind of a way to describe computationally the desired property, what you can do is goal-directed learning, where you kind of you sample some molecules from your generator, then you score those new design using a scoring function, and based on that, using reinforcement learning, you update your generator. The key consideration there is how well is this kind of scoring function correlated with the experimental endpoint. And I think like the trickiest part here is really to have kind of accurate enough scoring functions that represent like your endpoint reasonably well and correlate with that. And what my lab is working on is on sample efficiency. If we define an oracle as a computational prediction and simulation, then sample efficiency is how few oracle evaluations, oracle calls do I need to be able to kind of tune my molecular generator in such a way that it generates molecules above a certain threshold with the desired property profile. And what we've seen in drug discovery, but also materials design over the recent years, is you can have oracles with kind of that are super cheap to compute, for example, machine learning model. But typically, when you push them out of distribution with this novel property profile, they're not accurate enough to kind of give you the required information. Then you can use cheap simulations, for example, molecular docking or semi-empirical methods. But the goal would really to go towards more and more computationally costly simulations that correlate better with the experimental endpoint. And this is only possible if you are able to tune your molecular generator efficiently with as few oracle evaluations or like computer labels as possible. And to this end, we developed first augmented memory and then Saturn. Augmented memory was benchmarked on PMO, the practical molecular optimization benchmark by Connor Colley that was published in Europe's 2022. And what is kind of surprising there is that while augmented memory is based on of reinvent and still uses an LSTM as like the molecular generator, it's kind of it's performs better than much more advanced approaches in terms of sample efficiency. Those two here, the top performing models here, are really still recurrent neural network based. And the cool thing with PMO is that for the first time, they kind of put a restriction on the maximum number of Oracle calls that you could use to optimize your model. They fixed it to 10K, which is still kind of a lot, I would say, but at least it doesn't allow you to kind of go to, I don't know, 200,000 Oracle calls, which is completely unreasonable number. In the future, we should try to have be able to learn from, I would say, a few hundreds of labels, not more than that. More recently, we kind of decoupled augmented memory from reinvent and introduced Saturn and using kind of Mamba models instead, so state space models instead of LSTMs, were able to further increase the sample efficiency compared to the LSTMs. I think the interesting point here is that in literally every other field, you could go from LSTMs to transformers, see some improvements, but here in the sample efficient molecular design, we couldn't get much better results from a transformer model. But then with Mamba, we got surprisingly interesting results, and we could kind of here I'm just showing yield and the oracle burden. The yield is like kind of in this multi-objective docking optimization is how many in 1,000 oracle calls, how many molecules do you find that satisfy the property profile in those 100 calls? And the Oracle budget just tells you how many calls were needed until it was able to identify the first molecule that satisfied the property profile. And we can see that we are now kind of pushing towards the limits of kind of being close to 100 simulations needed, and we get within 1,000 Oracle calls quite a lot of candidate molecules that are interesting. What we also observed is kind of cool behavior in the observation, which we call top and locally explore behavior. While kind of recurrent neural networks were kind of always almost globally exploring, we saw after every kind of epoch when we were we saw that the Mamba model would kind of take a step towards a good direction and then again explore the molecular space there more locally and then again take kind of a step. You can also see it here where you have on top intra-chunk similarity, and on the bottom inter-chunk similarity between two epochs. And you have kind of almost a global exploration phase, which for the recurrent neural network was almost the whole kind of trajectory. And then you have this more local exploration and hops, which is kind of an interesting behavior to observe for those molecular generators. Now we can reuse with Jeff. We mostly explored like drug discovery related tasks, but we can reuse this sample efficient molecular generation framework, for example, for the Morita-Baylis-Hellman reactions to design kind of an organocatalyst for that. And there we will kind of really thankful for this publication here, where they actually introduced a scoring function based on the reactants and the rate limiting transition state that we could reuse in our kind of experiments. And they also experimentally validated that work. And compared to the GA that they had used in their publication, we were kind of with 1/10 of the Oracle budget, we were able to kind of find and generate new catalysts that were better than what they have found over 10,000 Oracle calls. And just to give you one kind of one visualization of the best catalyst we had found in one of the runs, you see it here how it stabilizes like kind of the transition state, like kind of the better it stabilizes that transition state, the less energy is required to make that reaction happen, and kind of the more performant is the catalyst. And what is really surprising here, and this is, I think, like what kind of I love the most about this work with Serena, is that kind of we are generating smiles, which is like a 2D kind of 2D representations of molecules, but through the scoring function, this goes through a simulation where like we compute the 3D coordinates and re-optimize like the reactants and the transition state. And through this like float value it gets back from this 3D kind of from the simulation, the 2D generator is able to learn 3D functionality, and it learns to generate those bifunctional organocatalysts that have like this amine, the hydrogen bond donor that stabilizes the transition state, and in between an exactly like super well placed rigidified linker that makes it possible for the hydrogen bond donor to like kind of be at the exact spot where it's most useful. So kind of we're generating in 2D but learning a 3D function. This, yeah, still surprises me. One kind of thing that we need to have if we want to have some impact globally is we need to be able to synthesize those molecules that we just virtually design. So, and synthesizability has been a bottleneck in this field for some time. So, what we demonstrated as well with Jeff is that this was recently published in Chemical Science, like that Saturn is sample efficient enough to kind of connect the score to a retrosynthesis model. Retrosynthesis is just a model that gives you a path from a target molecule to commercially available building blocks and connects those commercially available building blocks with reaction steps to combine them together until you get that final molecule. And now we are kind of sample efficient enough to actually directly optimize for desired properties, but also for having a synthesis route to that target molecule. But we went even a step further and said, like, this might eh, taking all commercially available molecules into account might be too much. Sometimes you're in a situation where kind of the lab has a specific set of molecules available and wants to start from those, or you could also imagine that you have bio-based building blocks, that a set of bio-based building blocks may be derived from wood, and you really want to kind of generate your novel molecule using those building blocks. And in some recent work, it's still a preprint. We kind of showed that we can now also enforce specific building blocks in the routes that we found to the generated molecules. And this is kind of super challenging to do because, like, if you say, okay, I generate molecule and I only reward the model if I find a route, then maybe you can still have kind of a dense reward. But if you say, I give it reward when it's a route, plus the route contains some specific building blocks that we want to have in the route. This turns into an extremely sparse reward landscape and makes this optimization unfeasible and with limited budget. So what Jeff had to come up with is this Tango reward function that you see here that combines Tanimoto similarity, like a similarity between current molecules and kind of molecules in the tree, and also some substructure match to kind of steer the generator towards that set of building blocks that we want to use in the runs. And here's just some results. So we can kind of define some sets of building blocks, very small ones, or also larger ones that you could kind of a typical use case of that would be, for example, late stage diversification and optimization of a hit. And based on that, we can kind of find newly generated molecules that contain those substructures, but also have quite an interesting property profile at the same time. If you want to read more into like de novo molecular design, we have a recent review on that. And I think one of the nice things in that review is that we collected all the different experimental validations that existed up to that point. And there were kind of more than 40, I would say. And Jeff is continuing to just add to this GitHub repository here all further experimental validations that we find. So you have the up-to-date version of that table here on this GitHub repo. So now, like kind of, we already talked a bit about synthesizability, but language models were also used to kind of build machine learning algorithms towards predicting synthesizability. And if we look at the trends of the recent years, we see that back in 2018 and so on, I think from 2016 on, we had some language models working on single modality, like for reaction prediction, retrosynthesis, reaction condition predictions, and so on. And we saw this kind of trend towards using multiple modalities and say, hey, can we convert now a chemical reaction into something else, like for example, here a recipe to make that chemical reaction work. And this was some work together with Alain Vaucher at IBM Research. And more recently with like GPT and so on, kind of we worked a lot more on how can we make general purpose language models useful for chemistry with Kevin Yamlonka on like can we fine tune large language models for different tasks in chemistry, and yeah, last year with with my team at EPFL, like kind of what can we, how can we make them better at chemistry if they have some deficiencies more through in context learning? And there are plenty of other examples like that. For example, Co-Scientist by Gabe Gomez or Clarify by Alanis Bulguzek Scoop. But for the next few slides, I will talk mostly about ChemCrow and augmenting language models with chemistry tools. This is joint work with Andrew White and Sam Cox, Ollie Schilter, and Carlo Baldassari. Andrew and Sam are now at Future House, and they are continuing to like build more crows. Yeah, back when we started this work, we yeah, ChatGPT was really bad at chemistry. It gets better now. Like some commercially available models are getting better and better at chemistry, but back then they were incredibly bad. As soon as we would push them slightly out of distribution, they would just confidently hallucinate. But we had plenty of excellent chemistry tools available. Some through APIs, some hosted on GitHub repository and so on, somewhat living in isolations. So what we came up with is ChemCrow, and crows because they are known to use tools very well, and we kind of added tools to a language models from like the molecular side, most of them like calculating some properties, comparing two molecules, looking if they are similar, modifying them, checking the functional groups, checking the novelty, and so on. Then we had some general tools, like you would also always do literature search, paper QA, web search, code, and the human expert, then some reaction related tools, and in the end, also some safety tools to kind of put some guardrails on top of that model. And given that, we could now just give a simple prompt to the system, and instead of just hallucinating an answer that was incorrect, it would start thinking about the problem, selecting the action that would give it the most useful information to solve that task, generating the action input. It's everything is text-based, so it kind of has to generate the input to that tool in text. You can then do the cool thing here is that then within the tool you can do whatever you want. You could convert a 2D representation of a molecule into a 3D structure, run some simulations, as long as what you return from that tool is back in text, which the language model can observe again and then reiterate until it comes to a final answer. And one of the test cases that we had there was this plan and execute the synthesis of an insect repellent. And there, kind of the language models first had to identify what is an insect repellent and search the literature for it. Found DEET and a few other options. But if you think of DEET, this is kind of an abbreviation and doesn't contain any structural information. So it's kind of incompatible with a lot of the other tools. So what it selected as a second action was the name to smiles tool to get back the structural information of that molecule. Then it went on and used the reaction planner tool that queried the reaction for chemistry API from IBM Research I had worked on previously to get a synthesis route and to convert this synthesis into like recipes. And in the end, because we had connected it to a robotic platform, after kind of 2 hours, we could confirm that our language model agent had actually synthesized it. And I think this was one of the first demonstration of like simple prompt to like the actual execution on a robotic platform. Just to show you the robotic platform. I'm not sure if I'm sharing this sound at the moment correctly. Uh, I hope you hear it, but yeah, it doesn't matter too much. I would say like kind of, but this is just to show you that this platform actually exists and the approach exists. We also kind of ran a few other test cases in like for thyrea, organocatalysts, and also in the future we plan to work with the SwissCat Plus team at ETH Zurich and EPFL to kind of further like optimize those large language models for chemical research. This is one interface that exists for ChemCrow, where you can see it in action, how it queries the different tools and kind of selects one, generates the input, then yeah, gets back a prediction and so on. I think like ChemCrow is super modular. The tool set and LLMs can be changed and improved. Back then, when we worked on that, we started working on it pre GPT-4, and GPT-4 got us a significant like kind of performance boost. But now we would definitely go for like a more open model and to kind of maybe we were quite general in the tools that we added to the model. And I think like it would make sense if you have a particular application in mind to like make this tool set really focused and specific for that particular application. And we have also more use cases in the paper. One challenge that we always faced is kind of benchmarking. It's really hard to benchmark LLMs in chemistry and specific topics. And here I just wanted to highlight one work with Kevin Jablonka, led by Kevin and his lab, where we contributed and where we built ChemBench, that has kind of more than 2,700 multiple choice questions that in the big bench format. And the cool thing there is that we kind of gave those like a reduced set to plenty of humans and kind of compared have a leaderboard where we compare human performance with the large language model performance. What is striking is that particularly like kind of the closed source models seem to perform really well in chemistry, but all very, very large open source models. But I think like this is a more up-to-date version. Like when we were looking at that initially, like kind of in the first version in the preprint, like they kind of like only kind of the top close source models were kind of showing good performance in chemistry. We have different classes, and we see a bit where the different models like perform best. And we also the human experts could use tools if they wanted, like calculators and so on. And we compared the kind of the performance with and without using tools. But my question is always, is multiple choice really what kind of, how does being good at answering multiple choice questions really map to the real world performance that we are interested in? And kind of, I think they're super useful to those benchmarks, but maybe we need even kind of other more like stricter or harder benchmarks that go closer to like kind of real world applications. And with my team at EPFL, Andres, Theo, Daniel, and Zlatko, we thought a lot about using LLMs in chemistry. And what we could kind of see is that, okay, we can fine-tune them for property predictions. They are reasonable at multiple choice questions and build them into agentic workflows. But once every time we try to generate like specific SMIs that like those text-based representations that it cannot recopy from another from another tool or something like that, they end up doing a lot of mistakes. And this is not ideal if you have them somewhere in a workflow. So, but what we also observed is that even on reactions, chemical reactions, it could kind of now already like kind of produce some advanced reasoning on those, like kind of yeah, it surprised us and particularly Zlatko. Zlatko has a background in total synthesis and kind of we are often measuring like kind of how well our models perform with like how much Zlatko is excited about what we can predict. And he was surprised how well kind of the large language models could reason about given chemical reactions. So the strategy we came up with is to use them as chemical reasoning engines because now you have kind of a natural language interface. You can use a traditional search algorithm, which can be based on machine learning to provide different solutions, but kind of to score the different solutions and reason about those solutions, you can use kind of the LLM to kind of guide you to the best strategic solution. And we have two, in that preprint, we have two main use cases. One is steerable synthesis planning. Retrosynthetic tools can provide you often with 50-ish or like more solutions how you could get to your target molecule, but they contain very nice synthetic routes and very bad ones. And what typically happens if you give that software to an experimental colleague, they look at five of them, they find that four of them contain crazy stuff that would never happen, and then they say the machine learning model does not work. So here we turn it around. We let the expert like basically describe what he or she has in mind. For example, break pyrimidine in the early stage, but get all other rings for commercially available materials. And then we can kind of, the language models now can easily reason along synthesis routes that contain 15, 20 steps and really recognize whether this is actually happening or not. And this provides you kind of a good way of interacting with other tools. And here we have just different targets, different prompts, and what we observed is that really kind of DeepSeek surprised us with like the performance in open source and the Claude Sonnet models, even like Claude 3.7, are like kind of really strong in aligning kind of the prompt description with the actual routes. Here we just have like kind of an interface of one of the retrosynthetic tools that we are developing in the lab. Here you see this molecule and kind of this is now you can just add like late imidazole formation and kind of score on those different routes. Here it's a 0, but like you could re-rank according to the LLM score, and it actually kind of reasons about all the different steps and checks if the overall route kind of aligns with the initial expert query. And like that, you can, through all those X proposed routes, you can easily find what kind of what works for you. And we can also change to the early formation and get a high scoring route. And again, it kind of, you have the reasoning across all the different reactions and the final reasoning. And this aligns also super well with what our organic chemist, like kind of how he would rate those routes. The other use case is kind of we're now going for from a super large scale where you have like up to, I don't know, 26 reaction steps, to like looking at single reactions in more detail. And this would be a reaction mechanism elucidation, where you can basically describe a chemical reaction through a sequence of elementary steps. And for that, also, we built a small benchmark and kind of tested how well kind of the different language models would kind of prefer the actual like ground truth move over all the other suggestions. Again, you can kind of enumerate all the different possible elementary steps and rank them with the models and see how, if it's able to understand what would be the correct move. And we see again similar trends with the cloth models understanding chemistry quite well. And this is just to compare, like, without an expert description of the actual kind of reaction happening or with, and the better the model, the least improvement you get from actually adding this expert prompt to the input. In the end, I think I still have a few minutes left. Kind of I was talking about experimental validation at the beginning, and I have not shown too much experimental validation between like a few organocatalysts and the insect repellent. I just wanted to highlight some cool work by Bojana Rankovic, who is a last year PhD student and collaborated with an experimental group to kind of, on one side, like standardize their electronic lab notebooks, get all results that they had automatically through an API, and being able to use that in a machine learning loop doing Bayesian optimization. And what we kind of targeted is wanted to design copper nanocrystals with a particle shape. So one big topic that we have globally is CO2 and CO2 and how can we convert CO2 into, for example, a fuel. For that, like, copper is handled as one of the main materials that can do this conversion. But copper exists in different, you can make differently shaped nanocrystals, and different shapes have different reactivity. So would it not be amazing to be able to target a specific shape and so reactivity with a Bayesian optimization algorithm? And for that, we kind of, because shapes are just kind of labels by humans, we kind of converted the shapes into a continuous surface energy scale, which allowed us to target specific values in that scale. And what we observed is kind of like removing all the cubes, but targeting cubes, or removing all the tetrahedrals from the training data, but targeting tetrahedral shape. We could kind of find new synthesis routes or new synthesis procedures better to kind of get to the target shape. What is super challenging in the material space is really that you have not only one synthesis that leads to a cube outcome. Like in the dotted here, you see like kind of previous synthesis for cubes that we didn't include in training, but that we had in the database. And in black, you see a newly found synthesis procedure for cubes, and similarly also for tetrahedral. So it's kind of the ground truth is not unique. So and this makes it really, really challenging. But one cool result of that work that was recently published in JAX is that we were able to discover a new shape, which was previously never reported for copper. We knew it could potentially exist because it was observed in gold, for example, but never copper. So, like by targeting a specific value where this shape should be placed on the energy scale, we're like after 3 iterations able to first observe some rhombic dodecahedral, and then we use the output of the XOD analysis to continue to optimize the peak for that was representative for that particular shape. I kind of again a challenge would be that people groups could just report that shape just by like having a crop on iteration 3, but we kind of continued for many more iterations until we had like a clean sample to actually synthesize that. One challenge that exists here, and that a question that I often get is like, if we're in the low data regime in chemistry, what kind of, now I have this new reaction, I have this new procedure, I have like kind of Bayesian optimization would be very well suited for that, but what are kind of the input features that we should use? And they are like, without, yeah, there's just no way you don't have validation data to kind of decide about the input features without running costly experiments. So what we are currently doing is to kind of also explore LLMs so that can directly featureize whatever you want, a synthesis procedure, a SMICE, whatever. In previous work, we showed that they are performing reasonably well, but not competing with domain-specific representation, the two ones that you have here. Here, we're really using an LLM on top of a general kind of synthesis procedure where you change the different parameters that you want to change in that procedure. But what we kind of managed to do now, and the preprint will be out soon, is that we managed to jointly train an LLM and the Gaussian process, and we can, on plenty of data sets, we can show that compared, okay, here you have the domain-specific representations, and here you have the baseline, which is just the fixed LLM embedding, and we can get quite nice performance in BO by fine-tuning jointly an LLM while doing Bayesian optimization. And this is just a cool plot that shows you how the high and high, low and low, and high and low points separate. Like high and high comes together, low and low comes together, but high and low points like across the optimization kind of with 50-ish iterations get further away from each other. And here you also see how this is the fixed LLM kind of latent space, and it nicely structures along the different iterations. And also show very nicely calibrated uncertainty, similar to a GDP with a domain specific representation. And now we kind of we combine the benefits of the flexibility of the LLM with the uncertainty calibration of the GP. So with this, like, let me just conclude, because if you're interested in designing new molecules, I think augmented memory and Saturn are a super nice sample efficient way to do that. We've shown that LLM-powered agents could kind of at least yeah, to some extent, like kind of tackle chemistry tasks through ChemCrow. Evaluation is always challenging, but new LLMs seem to become better and better at chemical reasoning. And if you want to do experimental validation, BO is often a very good starting point. And if you want LLM-based BO, we'll soon have an updated preprint. So yeah. Thank you very much for your attention. This is the amazing team behind that work and the funding, which I'm very, very thankful about. And yeah, thanks a lot. And it was a pleasure to be here today. I'm open for questions.
Yeah, thank you very much, Felipe. And so I have a question from the audience. Is AI-driven synthesis a solved problem?
Okay, yeah, I think like kind of I didn't show that here, but let me check. Yeah, no, I would say like kind of if you if you go to like if you see those robots and they are kind of doing like you connect there are plenty of remaining challenges as soon as you involve a robotic platform because you're for example restricted to the building blocks that you currently have, the chemicals that are currently in the robot, and you can everything outside either needs to get ordered or like kind of you have to have a human replacing the currently available stock with something else. The synthesis planning models are still kind of now we get some nice results with this LLM reasoning on top, but plenty of the solutions that you just get out of the box do not make that much sense for chemists, and we struggled a lot with that in the past years. Um, yeah, I would say like kind of yeah, things that would be interesting to chemists would be more complexities like that, but we are far, far away from having automated synthesis from something like this. Yeah.
Okay, yeah, thank you very much. And there's another question or questions. Why are text-based representations so well suited for chemistry and would not graph-based representations be better suited?
I think like this is a question I get quite often. I think like we have both, like kind of we have in the team we have some people that are working more on the graph-based and 3D representations, others that are working more in this language space. I think like it's there was so much like the models, the base models that you get for language-based or text-based representations are, I think, a bit more mature, so it's easier to get kind of good results more or less with an out-of-the-box model there than when you go towards more graph-based and 3D-based models. And yeah, I think I would always include a text-based representation as kind of a baseline. But I'm also with some of the group members, I'm really excited about going beyond text and hopefully we'll have some work out soon. Yeah.
Okay, yeah, thanks, Felipe. And here I would like to close then today's session and appreciate all your attendance and see you soon in one of our next webinar series.
Thanks so much, Conrad. It's really a pleasure. Bye bye. See you.
Bye.